Go ahead, Mehmet.
Thank you, Dina. Good evening. I'm Mehmet Ansoy, Vice President of Denver Astronomical Society. This evening, we are delighted to have Dr. Monica Young as our guest speaker. Dr. Young is going to be talking about what's inside a neutral star. She has received her Bachelor of Science in Physics and Astronomy from University of Pittsburgh, and her PhD in Astronomy from Boston University, during which she conducted research at the Center of Astrophysics on the behavior of supermassive black holes feeding in distant galaxies. She left the academic world for her dream job as news editor at Sky and Telescope, where for the last 10 years, she has commissioned, written, and edited articles on the latest news in astronomy, science, observing, and technology. She writes and edits feature articles for the print magazine, as well, most recently, authoring How Old Are Saturn's Moons in the September 2021 issue. Dr. Young also, jointly with her digital team, completed a massive overhaul of the Sky and Telescope website. Dr. Young, please proceed with your presentation.
Thank you so much for having me here tonight, and thank you for that lovely introduction. Let me just say first, it's been wonderful just sitting in on this meeting and hearing all of the things that you are doing as a society, and the outreach and everything that you're doing. It's really wonderful to hear a club being so active and involved in its community. So I really enjoyed being here so far. I'm going to talk to you tonight about how we're using wavelengths that are beyond human perception to kind of explore some of the densest matter that we know of in the universe, the matter that's inside neutron stars. And this is matter that's beyond human creation. We cannot make this matter in a lab. We have to explore it out in the cosmos. Earth's atmosphere actually blocks most of the photons that are zinging around our universe. And even the photons that manage to make it into our atmosphere, we're not able to perceive all of those. So with the dawn of the space age, we've been able to send up satellites into space and access wavelengths that we haven't had access to before. So that's, I'll be talking today specifically about X-rays and how we're using X-rays to understand neutron stars. And with that, we're going to be able to explore some of these really strange, dense states of matter. There we go. So we're just going to begin at the beginning. So neutron stars are collapsed cores of massive stars that have gone supernova. And these are massive stars that are roughly between 7 and 20 times the sun's mass. These are the ones that their core, when it has run out of fuel to fuse, it implodes, but it stops at the level of where the nuclear force is what's keeping the core from collapsing further into a black hole. And so they shed their outer layers because those outer layers are actually falling in and they actually ram against this neutron star that has formed at the center. And then that the shock actually reverberates back outwards, and that's what throws off the outer layers. And that's the supernova that we see. And the supernova itself is actually extremely important because it's taking all of those elements that have been fused inside of the star and distributing them throughout the universe. So without supernovae, we wouldn't have planets, we wouldn't have life. But we're going to focus in on the neutron star that's left at the center of these remnants. And so what happens here is that about a sun's worth of mass, or maybe 2 suns worth of mass, collapses into a space that spans about the length of Manhattan. So these are city-sized compact objects. And they are really some of the most extreme things that we can find out in the cosmos. And they were actually discovered by their radio waves. In 1967 by Jocelyn Bell Burnell, who had constructed these radio receivers, and she saw these, she saw pulsars. She saw the pulses coming from jets coming from these neutron stars. So the jets were spinning past Earth in kind of a lighthouse fashion. And those were the kind of the pulsating signals that she found. But neutron stars actually do emit other wavelengths too. They actually do emit visible light. And although they're not very bright, and then they also emit more energetic photons such as X-rays and gamma rays. And so the Chandra X-ray Observatory, which was launched in 1999, turned its eye to this supernova shown here, which is Cassiopeia A, pretty much right after it launched, because this is one of the, this supernova only exploded about 380 years ago. So very, very recently. The neutron star is still extremely hot at its core. The supernova remnant itself is still expanding. I mean, we can actually watch it expanding over the years. And so it's an extremely fascinating object. And right away, Chandra was able to see the neutron star at its core. And so that was really neat, just a confirmation of what Chandra was capable of at that time. And I do want to point out here, though, that the Chandra does have really good spatial resolution. It actually matches like visible light telescopes in terms of what it can see. But although this dot does look very large, especially in the blown up image, this is actually just a point of light. So it's only able to see a point of light from the neutron star. I can't resolve that. But we can still get a lot of information about neutron stars from X-rays. And the reason that we want to focus in on neutron stars is because neutron stars are really just this side of collapsing into a black hole. They have immense gravitational pressure that squeeze the electrons and the protons together to form neutrons. And basically kind of this neutron superfluid within the neutron star. And that is the densest matter that we know that the cosmos can make. It's possible the cosmos can make something even denser at the cores of neutron stars, and that's kind of what we want to get at today. So to give you a sense of just how extreme neutron stars are, there's just have a list of little factoids that are kind of fun to throw out, especially if you're doing outreach, actually. If you brought just one pinhead of neutron star material to Earth, it would weigh as much as a battleship. Although you do have to think also, if you're bringing neutron star material to Earth, it's probably going to expand out very quickly. Would be rather explosive, but for the moment that you're able to put it on the scale, it would weigh as much as a battleship. So that just gives you a sense of just how dense the material is. Because of that immense gravitational pressure that's pulling everything together, neutron star surfaces are actually really smooth. The tallest mountain that you could get on a neutron star is only 1 millimeter high. So super smooth surfaces. And neutron stars actually do have atmospheres that are not made of neutrons. They're made out of whole atoms, so probably helium or carbon atoms. And the atmosphere can actually extend up to a few inches from the surface of a neutron star. So it's pretty compact, and it's not exactly the breezy atmosphere that you think of when you think of atmospheres. So the atmosphere of the Cassiopeia A neutron star is actually roughly as dense as a diamond, and it's made probably of carbon atoms to boot. So that kind of gives you a sense of these kind of extreme objects that we're talking about. And then finally, just escaping a neutron star requires speeds of about half the speed of light. So we're really looking at objects that are have the effects of relativity impacting what we see from them too. And so in recent years, there's been a lot of progress made, both theoretically, but also just observationally, in determining what neutron stars are made out of. And so just theoretically, we think that because of that gravitational pressure pushing protons and electrons together into neutrons, it's the nuclear force between neutrons that's basically fighting off the collapsing effect of gravity. And those neutrons even actually squeeze out of the nuclei. So you no longer have nuclei, you just have neutron, like kind of a neutron soup inside the neutron star. But it's not actually neutrons all the way down. It's probably 5 to 10% by mass of protons. And the protons basically keep things stable within the neutron star. And you kind of get different forms of matter as you go through. So if you look at the atmosphere, like I said, that's whole atoms. Then you have kind of a thin outer crust where you probably have just ions and electrons. So you have the nuclei, but you don't yet have the full neutron kind of superfluid. And so that doesn't actually start happening until the inner crust. So the inner crust is where you start to get those protons and electrons combining into the neutrons. And then by the outer core, you have also you have the superconducting protons in the outer core, but you have kind of this neutron superfluid throughout the neutron star. And then in the inner core, we have just a question mark. We're not really sure what's in there. So how do we know what neutron stars are? So what I mentioned earlier is that we were able to first detect neutron stars by their radio waves, and those come from jets that are coming out of the magnetic poles of a neutron star as it's spinning around. But when we look at X-rays from neutron stars, the X-rays are actually thermal in the same sense that when you look at human beings, the body heat that we radiate radiates at infrared wavelengths. When we look at neutron stars, they are so incredibly hot, about millions of degrees, that their surface actually radiates thermally in X-rays. And so when we're looking at the X-rays, that actually tells us about what's going on at the surface of the neutron star. So there are jets coming out of neutron stars, and the magnetic field channels particles into these jets that then escape at relativistic speeds away from the neutron star. And within those jets, you can get both particles and radiation interacting with the magnetic field, and you produce X-rays there too, as well as radio waves. But these are called non-thermal X-rays. They're not produced by the heat, they're produced by other processes that are going on. But at the base of the jets that are coming out of the neutron star are hotspots, and that's these kind of light blue areas here. So those hotspots are producing thermal X-rays. So you kind of have one of two scenarios. Either you're producing X-rays from all over the surface, or you're producing X-rays from these hotspots at the base of these jets. So we want to be able to capture those X-rays so that we can study the surfaces of the neutron stars. But in our everyday experience, we know that X-rays are kind of hard to catch. How we experience X-rays in our everyday life is probably through medical X-rays. And there you're basically shooting a whole bunch of X-rays at something. Some of them get absorbed, such as by the bones here. And some of them just pass right through the materials, such as through muscles and skin. And so how do we take those kinds of X-rays that either pass straight through something or get absorbed? How do we force those photons to focus? So when we look at visible light, we just take a mirror, right? Or we take lenses, and we're able to use that to pretty significantly bend the path of light. And it turns out you can bend the path of X-rays. But the bending happens at a much more subtle level. But you can do it with sets of mirrors. So X-rays bend at grazing incidence angles. If they're grazing incidence, meaning very small angle relative to the material that they're reflecting off of, you basically get an effect like skipping a pebble across a pond, where the X-rays do reflect, but just very, very subtly. So you can kind of combine these mirrors, and this design combines paraboloid mirrors with hyperboloid mirrors, and then kind of channels the X-rays over to a detector that would be over here on the right. And so if you have any one set of mirrors like that, you're not going to be able to catch a lot of photons. So the solution to that is just to nest multiple mirrors. So in the case of the Chandra X-ray Observatory, they nest 4 sets of these mirrors. And so this is kind of the diagram of how that looks like. And then this is what it looks like in practice. So they have a giant mirror, a set of 4 sets of mirrors, sorry. And these are coated in gold, and they are polished until they are super smooth. So if X-rays come against anything, they're basically going to just smash into it. They're either going to be absorbed or they're going to be passed through it. And so you really, to get that grazing incidence effect, the mirrors have to be very smooth with bumps no more than a few atoms high. And if you consider that a human hair can be roughly 500,000 atoms wide, that kind of gives you a sense of like 100,000th of a human hair is the kind of the level of smoothness that we're talking about for Chandra. But there are other telescopes, X-ray telescopes other than Chandra, and one of these is specifically made to look at neutron stars, and that is the Neutron Star Interior Composition Explorer, which is perched on the International Space Station since 2017. And so this is this little box here. So the solar panel is rotating in the background, so that's what you're seeing there. But this little box here is looking at different parts of the sky with all these little circles here. Each one of these circles is an X-ray collector. and then it collects the X-rays and then puts them back towards the detector, which is at the back of the box. And what NICER really excels at is catching photons and then time stamping them, saying exactly when those photons arrive to within 100 nanoseconds, which is what you need if you're going to watch these city-sized pulsars that spin around faster than blades in a kitchen blender. And so this is a close-up look at NICER. So there's 56 of this X-ray collectors that it has, really X-ray telescopes. And each one of those collectors has 24 nested mirrors. So a lot more nested mirrors, but they're not quite as smooth as the ones for Chandra. So the resolution that NICER gets isn't quite as good. It gets 5 arc minute rather than 1 arc second, which is what Chandra gets. But NICER is basically looking at the brightest sources in the sky, which are pulsars, and it can especially identify them just by the fact that they're pulsing. And so it doesn't really need good resolution. It really just needs that ability to timestamp the photons. So all of these 56 X-ray collectors and each one of their 24 nested mirrors work together to kind of image a full hemisphere of the sky at a time and record lots and lots of data on these pulsars. And so NICER is basically by getting these pulses from pulsars, from spinning neutron stars, it's basically able to get at get high enough accuracy on the pulse profile that it's able to investigate details that haven't been able to be investigated before. So one really neat thing about neutron stars is, as I mentioned, there's so much gravitational pressure there that there's actually relativistic effects. And so NICER, when it's looking at neutron stars, is not only seeing the photons that are coming from the surface that is facing NICER, it's actually seeing some of the photons that are coming from the opposite side. But as the photons leave the surface, the path of the photon is bent just by the strong gravitational field. And so the path of the photons actually bent around to reach NICER. And so this is really crucial to what NICER does. And that's demonstrated in this diagram. So if NICER were looking at an object with no strong gravitational effects, and it saw this hot spot going around and then disappearing through the back end, where if you measure the brightness over time, you see it get brighter as the hot spot comes in front. And then as the hot spot goes in back, it just goes to 0. And we wouldn't be seeing any light at all from the neutron star. In the case of neutron stars, though, with the strong gravity, then you have you can actually see the hot spot even as it goes behind the pulsar. So you see the brightness go up and then come down, but then it never actually gets to 0, because even when it's behind the pulsar, some of those photons are still bending around back towards NICER. And so the amount of photons that get bent around, the amount that you're able to see behind the pulsar, that basically tells you something about the mass of the pulsar that you're looking at. And then looking at how the hotspots are going around gives you an idea of the radius. But it does get really complicated. So there's more than one hotspot, right? Because there's usually at least 2 jets coming from a pulsar. The spinning, because the neutron stars are spinning so quickly, they actually get kind of this spread out oblate shape to them. And so that can kind of complicate matters if it's not an exact sphere that you're looking at. The composition of the atmosphere of the neutron star, stuff like that, can also affect the observation. So there's a lot of details that have to go into this modeling that astronomers do. But ultimately, what the goal is, by looking at these pulse profiles, we're actually able to see what's happening in the core of a neutron star. And the way we're able to do that is by comparing the mass of the neutron star and how that changes with radius. So if there's a couple of different things that could be going on in the core of a neutron star. So it could be that it's just neutrons all the way down with that smattering of protons, but mostly neutrons all the way down to the core. And in that case, as you put more mass onto the neutron star, it's going to get larger, right? But it's possible that in the core, the density could get quite high. And the idea that depending on the neutron star, they get different answers, but it could be, it's definitely more dense than an atomic nucleus. It could be twice that of an atomic nucleus. It could be 5 times that of an atomic nucleus. But it gets incredibly dense at the center of a neutron star, really beyond the level that we're able to measure in labs on Earth. And certainly, even if we can get high enough density on Earth, we can't get high enough density at that temperature. So the lab experiments they do on Earth only get to like really dense but cold plasmas, not to the level that they are in the heat that it experiences in neutron stars. But it's possible as the density increases, and especially with that heat, with the temperature being higher, it's possible that things might actually break down further in the core than they do in the outer layers. So one possibility is this one on the left here, is that we could have a quark core. So every neutron is made out of 3 quarks that are tied together with gluons, and its neutrons are made out of up and down quarks specifically. So if those break apart, then you might end up with this core that's just made out of up and down quarks that are separate, no longer tied together into a neutron, but just kind of this compact soup of quarks. It's also possible that these quarks could themselves transform. So you could have an up or down quark transform into a strange quark. And that forms what we call hyperons. So hyperons are not theoretical, they are actually a particle we have observed, but lab experiments can only make hyperons very briefly. So in a neutron star core, it could be that these hyperons exist for millions of years. And so if they're stable on that level, that could affect how the mass or how the radius changes with mass. And then finally, a third option is that things could break apart even further and kind of rearrange themselves. So you end up with these 2 quark particles called kaons. So kaons, again, have been observed in the lab. This kaon, what's called a kaon condensate, has not been observed. That's theoretical for neutron stars. And so these are basically just 2 quark particles where one of them is strange. So it could be strange up and then strange down. But basically, the idea here is that you can get various types of exotic matter, and we don't really know what's going to happen, because while we do have theory that explains how quarks and gluons make up subatomic particles, that theory, the quantum chromodynamics theory, only actually works for a couple of particles at a time. So when you talk about a neutron star, where you're talking about basically a giant atomic nucleus, but made out of millions of neutrons and some protons, various things can happen, and it's kind of a wide open playing field. And because we don't have the lab experiments that can really investigate that kind of situation, really the only place we can turn to test that, the different assumptions and simplifications that go into trying to explain neutron stars, is we have to actually observe it. So that's what NICER does. So NICER looked at 2 pulsars, I think within the last year, and we wrote news stories on them separately for the Sky and Telescope website. But basically the idea is that they looked at these pulse profiles, and then they modeled what they thought the hotspots looked like on the neutron star itself. So in this case, this is pulsar J0030, and based on the pulse profile, they figured that this neutron star has about a mass of 1.3 or 1.4 times that of the sun, and its radius is roughly 13 kilometers. So there's 2 independent teams working on this, and they both got roughly the same answer. And you can see why when you look at the models of their hotspots. They look a little bit different. One has 3 hotspots and one only has 2. And the one with only 2 has this long crescent shape to it, and then a circle, versus this is kind of a shorter shape and then more of an elongated shape there on the other end. But overall, if you look at them spinning around, they actually look pretty similar. And so it's not surprising that the 2 teams got similar answers for the radius and the mass of these neutron stars. Then there's this other neutron star, J0740, and this one is kind of on the opposite extreme. Whereas this one was 1.3 solar masses, this one is 2.08 solar masses. And so this is the neutron star, the most massive neutron star with a highly reliable mass measurement. And again, two teams looked at the NICER pulse profile for this spinning neutron star. And they came up with these models. And I'm sorry, the movies start at different times, so it's difficult to compare them exactly. But they basically came up with very similar ideas of where the hotspots are on the neutron star surface. It came up with slightly different radii from the two teams. 12, one came up with like 12 and a half, and then the other one about 14 kilometers. And here's where it gets really important, that we're measuring the mass and the radius. So different mass and radius combinations basically tell us what's happening in the core. So if it's neutrons all the way down, then as you add more mass onto the neutron star, you're basically just going to make it bigger because it can't collapse anymore. So these are generally referred to as stiff models. And in this plot here, there's a couple of different options, but it's basically nucleonic 1 or nucleonic 2 are the neutron stars, or neutrons all the way down. So that's the blue line here, blue line here, and blue line here, and then these 3 red lines here. Then there's the possibility of more exotic particles in the core. And if that's the case, then as you put more mass onto a neutron star, then transformations happen within the core, and it's going to be able to compress further as those transformations happen. And whether it's a kaon condensate or a hyperon or whatever is happening, you get different options for how much the core compresses further, but still without collapsing into a black hole. And so these are kind of encapsulated here by the purple dashed lines. Here are the quark model. The blue is kind of a hybrid model that combines a couple of different options. And then there's the hyperon model, is this black dashed dotted line here. And so basically we have these 2 pulsar measurements from NICER, and they're different, pretty different in mass. One's 1.4, one's 2.1 solar masses, but the range of radii that are possible for these 2 neutron stars, as far as NICER can see so far, is pretty much the same. And so just based on that, it seems that neutron stars do seem to be fairly stiff, in that they don't really doesn't prefer a model where things kind of squish further in the core, but it doesn't really rule them out either. You can see a lot of the more exotic models still are able to match both of them. And so there's still more work to be done, but that's kind of really encouraging that we're able to just based on watching a pulse profile very exactly using NICER, we're able to already rule out some different models. Another neat result from NICER actually has nothing to do with the cores, but it has to do with how we look at artistic interpretations of neutron stars. So there were a couple of the images in the movies that I showed earlier on kind of show this bar magnet field, where you have a north pole and a south pole, and the magnetic field lines connect the two. Based on what NICER has seen of pulsars so far, that's completely untrue. So both of the pulsars that NICER has investigated, the hotspots they saw, there were multiple hotspots in the same hemisphere. And so that can't possibly be a dipole. There have to be tangled and multiple poles and things going on with the pulsar. So this is one example here that shows the field, the kind of the complicated field lines where maybe this here and this here are both hotspots. And there's a lot of other chaos going on. So this is probably more realistic when it comes to neutron stars, although you'll probably still continue to see the dipole interpretations of neutron stars, in popular media. But so there are other ways besides NICER and looking at pulses. One thing I don't think I mentioned earlier, but I meant to, was the Cassiopeia A neutron star. Actually doesn't pulse. So it radiates X-rays from its entire surface. And there is another neutron star that does that too. And this is in the center of this supernova remnant, Hess J1731. This is further away than Cass A, it's also older. But basically the idea for this neutron star, astronomers observed this neutron star and they figured it's not pulsing. It must be emitting X-rays from its entire surface. And so by modeling just the spectrum of this neutron star, they were able to get a mass and a radius and put it basically on the same plot. So this is the J0740. So this is the more massive neutron star here that NICER looked at. This is J0030, which is the lighter neutron star that NICER looked at. And then there's this one, and this appears to be the lightest neutron star that we know of. It's about 0.8 solar masses. And I do have a question mark on this slide because it's still not entirely sure that we've really measured the mass accurately for this neutron star. But if we have, it's a really curious result because, like I said before, like the mass is pretty different for these two pulsars, but the radius is about the same range for the two. Whereas this one, this is much lighter, and it's also a much smaller radius. And so what that means for this particular neutron star, the researchers actually suggested that it could be a neutron star, and it would have 0.8 solar masses, which is really odd and not really explainable by our ideas of how neutron stars form. Or it could actually be what they called a strange star. So it's actually already made out of this exotic material. And so there is reason to doubt this result, and that's something that the researchers acknowledge themselves, is that it is a very uncomfortable result to get something that's so light. And the reason for that is that neutron stars don't typically form with 0.8 solar masses. Usually, if a star like the sun, for example, runs out of fuel to fuse in its core, it becomes a white dwarf. And you usually don't get to that transition between white dwarf and neutron star until about 1.3 solar masses. And there's ways to make that a little bit smaller. So we do have a mass measurement for a neutron star that's only 1.2, but having only 0.8 solar masses is a little bit uncomfortable for most people. And so not everybody believes this result, but it does throw some interesting options in terms of what neutron stars could be made of. Maybe some neutron stars are made out of this strange matter. So stay tuned. Maybe there will be, there need to be more observations of this object to kind of corroborate these findings. So there is another way besides X-rays to look at neutron star innards, and that is by watching two neutron stars as they smash into each other. And so far, we haven't had a huge amount of ability to do that, but gravitational waves give us that potential to watch two neutron stars merge and kind of reveal what's on the inside. And so this signal that I'm showing here at the bottom of the screen here, this is the gravitational wave signal from two neutron stars that smashed into each other in 2017. And they were able to follow up right away and get just light observations of these neutron stars. And but just by examining the gravitational wave signal, they can actually understand what's happening as these two neutron stars come together. So generally, like in the beginning, when the two neutron stars are coming towards each other, they're emitting gravitational waves. And as they get closer and closer and they're spinning more and more quickly, they're going to be emitting gravitational waves of higher and higher frequency. And right in that last second before they actually merge with each other, that frequency jumps up really quickly. And in that last second, you can actually, depending on how much the neutron stars deform as they come together, which again goes into that, are their cores stiff or squishy? Are they made out of regular neutrons, or are they made out of exotic material? And so depending on what the neutron star cores are made out of, that's going to affect how much they deform. So they actually took this gravitational wave signal, and then they put it against the same equation of state kind of plot. So this is kind of a more stylized diagram that comes from NASA. But again, it shows the two pulsars that we talked about. So that these are the two NICER pulsars. And then this is the gravitational wave signal. So you can see that the NICER pulsars both prefer this kind of stiff matter model for what's inside the neutron star. The gravitational wave signal kind of allows for maybe it could be squishy, maybe there is something exotic going on in their cores, but doesn't really distinguish between the two models. So as of yet, those observations are not decisive. There were actually two other events in the third observing run where they looked for these gravitational wave signals. And there were two events where a neutron star collided with a black hole. And unfortunately, those signals just didn't show the same kind of, it weren't powerful enough, and also didn't go all the way in the same way that two neutron stars would. They weren't able to see the deformation as clearly, and couldn't make really any definitive findings from that. So far, we only have this one data point, but that's going to change. So just like a decade ago, anybody studying neutron stars really had to go based off of, well, what can we do in the lab and what can we do in theory? And now within this past decade, and really within just like the last year or two, we've been making huge strides in terms of what we can accomplish in terms of looking inside neutron stars. And so one of these is NICER, and NICER is going to continue operating on the International Space Station until the International Space Station falls out of the sky gently. And that is scheduled for 2030. Probably NICER won't be operating all the way until 2030 because it is going to be decommissioned earlier than that. But NICER actually has a whole target list of pulsars that it's looking at. So we have results from 2 of them, but there's 7 or 8 pulsars that are on that list that it's going to continue looking at. And it takes a lot of time, not just to collect the data, but also just to analyze it and figure out where are these hotspots, what do they look like, and have we taken everything into account. So NICER is one option for continuing to look at what's inside neutron stars. And the other one is gravitational waves. So we now have 3 gravitational wave observatories that are operating on Earth. So there's LIGO, and LIGO is based in the US. There's Virgo, which just came on fairly recently, and that's based in Europe. And then there's also CAGRA, which is based in Japan. And CAGRA only came online at the end of the last observing run. And so we have actually a new observing run coming up where they're going to be looking at gravitational waves. And that starts in March of next year, March 2023. And they've been making changes to the detectors to improve the sensitivity. And they are expecting far more. I mean, we're definitely going to get a lot more of these black hole merger detections that we've already had, several dozen of so far, but it's going to start getting up into the hundreds. And then we're also hopefully going to catch more of these neutron star mergers. So far, we only have one really strong signal that we've detected, but hopefully with a higher sensitivity and more detectors operating, we'll be able to see more of these events. And it takes a little bit of luck too. And then just the future of X-rays is also strong in terms of being able to understand not just the pulses, but just where the X-rays are coming from and how well do we understand even just the formation of the X-rays, and then how we can then use that to understand neutron stars. And so NASA has an X-ray mission operating currently. It's called the Imaging X-ray Polarimetry Explorer, or IXPE. And so IXPE is flying now. It launched last year and it's gone through, it has some preliminary results out now. But basically what it's looking at is the polarization of the X-ray light. So just like in visible light or at other wavelengths, light's always vibrating in different directions. So sometimes it's vibrating up and down, sometimes it's side to side, et cetera. It goes around the clock, so to speak. And when light interacts with magnetic fields, as is often the case around neutron stars, it can get polarized, meaning that it vibrates preferentially in one direction or another. And so what IXPE can do is actually look at this polarization of the light of the X-ray photons, and then use that to kind of investigate, where are the X-rays coming from? Are they really coming from the surface? And what does it look like on the surface? Maybe they can model like, is the whole surface radiating X-rays, or is it just parts of the surface? And that's really crucial when you're trying to understand, if you're trying to model the mass and the radius of these objects, you need to understand, what's producing the X-rays. Another mission that's launching soon is called XRISM, or at least for now. So that's X-ray Imaging and Spectroscopy mission. And this is actually a replacement mission. And you may all have heard of, or maybe not, but it was this short-lived mission called Hitomi. And Hitomi launched a few years ago and unfortunately had a software error that caused it basically to spin up while it was in orbit and basically fly apart. And so that destroyed this mission and only had the chance to really make a couple of observations before it basically flew apart into little pieces. And so XRISM is basically the replacement mission for Hitomi. And so once XRISM launches, we're going to have a lot of imaging and a lot of spectroscopy of sources, for example, like that lightest neutron star, that will give us a better idea of what's going on there. And then finally, in terms of X-rays, there's the kind of a successor to Chandra, although hopefully Chandra will operate for many years. But Athena is the European flagship mission that would basically be the successor to Chandra and give us those kind of similar capabilities. And that's launching in the 2030s. So the future is bright for our understanding of neutron stars. And I think it's going to be really interesting to see how this continues to progress, from basically no information on neutron star interiors to really understanding, what these really incredibly strange and dense objects are made out of. So with that, I'll take any questions. Maybe I'll stop sharing, and then we can have a conversation.
Thank you, Dr. Young. This was a very informative presentation.
Yes.
So we have, I think, several questions here in the chat line.
I see them in the chat, yeah.
Let me start with okay, I'm not necessarily seeing them in the order, but Ron is asking, do neutron stars cool down over time? That is, are there any dead neutron stars?
No, neutron stars have no real source of energy. They just have a way of stopping gravitational collapse, which is the nuclear force. But yeah, they have no real source of energy in the sense of like fusion. And so the light that we see from them is it's the thermal, so like the heat from the neutron star, and it's also the magnetic fields, just the presence of this very strong magnetic field. Eventually, neutron stars slow down their rotation, and then they're basically leaching energy from the magnetic field as they slow down. So, but yeah, so it takes a very, very long time, but they do eventually cool down.
I think Dina is asking, is there any conclusion or leading hypothesis about what happened to the leftover material from the neutron star collision witnessed in August 2017?
Like the light that we saw from it, like the material. So I think what happened is those two neutron stars merged, and so now they're a single neutron star. I'm trying to remember. I get different things mixed up, but yeah, that one didn't become a black hole, I don't think. But yeah, so it was right. We just saw the light from the merger itself, but it's really, really far away. And so I don't think that we can see light from it currently because it's neutron stars are not that bright. Like we can see them in our own galaxy, but it's difficult to see them elsewhere. So
Right. Well, I ask because I actually wound up doing a presentation for quite a long time at Chamberlain Observatory about it. It intrigued me, and I gathered all the information I could. And it seemed like it was about 3 weeks of a period of time where scientists could collect information about it. And there was a large amount of material that was spewed out by the collision, but I don't know if it was sucked back in. That's kind of what I was wondering about.
yeah, that's a good question. I mean, I think the material spewed out was through the jets, right?
No,
Or-
it was
or was
my
it the
understanding that it was by the collision itself.
Okay. Yeah, I guess I don't know as much about that. So I don't know if I know the answer to that, but I do get the sense I haven't heard of any other more recent observations of it. So I don't think we're still seeing the light from it. But that's a great question. If the material continued outwards or reaccreted, that's a good question.
Okay, thanks.
Steve Barr is asking, and do strange quarks carry a charge, as is the case with up and down quarks? Do you understand the question? I don't understand the question, but Steve, do you want to expand on your question? Steve Barr?
Okay, yes, I was just wondering, because I think the comment was, did you make a comment? If you didn't make the comment, then I misunderstood something, that a up and down quark can become a strange quark. Okay, in a neutron star, and I believe the up quark has a plus 2/3 charge and the down a minus 2/3 charge. Thus, two ups and a down make a proton, and two downs and a up make a neutron.
Right, right. Yeah. That's a good question. If the strange carries a charge, it would be it's two stranges and an up, right? Is what, let me just look at that slide again.
I think you had a couple examples where there were whatever, a strange with an up and a strange with a down.
Yeah. Oh, yeah. So the two particle ones are, or so that the two quark particles are kaons, and so yeah, then it's strange and up and strange and down. I don't know what charge the kaons have, if they're neutral or not. And then the hyperons were two stranges and an up, although it also shows two stranges and a down, so maybe hyperons can be both. Yeah, that's, yeah. I mean, it's weird stuff, right?
Yes, indeed weird.
Yeah.
That's why it's called strange.
Exactly.
Let me ask a maybe simple or maybe a dumb question. Why would neutron stars have electromagnetic field if they are neutrons?
Yeah, no, that's a good question. I mean, it's not all the way neutrons, right? Because it's like 10% are protons by mass. And then there's an equal number of electrons. So neutron stars as a whole are neutral. Sorry, my brain, I'm like, it's late for me. My brain is not fully working anymore, but they are as a whole neutral, but yes, they can still have magnetic fields because you have the protons and electrons that exist within it.
That's what I thought. There is another question from Dina asking if Earth had been close enough to a neutron star collision for humans to see, would it have been safe as compared to a supernova? How safe is it to be close to a neutron star?
Well, I think a neutron star by itself would be all right. I think you'd have to get fairly, I mean, they're very extreme, but they don't have, unless you're, actually, that's a good question. If it has if it's a pulsar and it has those jets of material, you probably don't want to be in the path of that jet of material very close. How close you'd have to be for that to be a problem, I don't know. Yeah, the neutron star collision, though, I mean, that emitted, across the electromagnetic spectrum. I mean, what I'd be really concerned about are a large amount of X-rays and gamma rays. So, like a gamma ray burst, for example, would be very bad for us to see within like 1,000 light years. If
actually
neutron star merger generates that amount of gamma rays, though, I'm not sure. So
actually, Ron is asking a related question. You mentioned that neutron stars are sources of X-rays. Do they emit photons at other energies, such as at gamma rays?
They do actually emit gamma rays, and you can even see pulsars that pulsate in the gamma rays. And so, but those are that's gamma rays that are generated in the jets that come out of the neutron star. So that's the thermal emission from the surface of the neutron star really can only be X-rays. But yeah, absolutely, they do generate gamma rays, radio waves, visible light. They kind of they span the spectrum.
Chris Hudak is asking a similar question that I had in mind. Early in your presentation, you stated the highest mountain on the surface was only probably 1 millimeter. How will you be able to measure that?
Oh, that's a good question. I don't know.
I mean, how do you assess that it would be so small or so tiny?
Yeah, I think that's it's not something you could measure, right? But I think that's just a theoretical, if the gravity is this high, how much could the material actually move? And the answer is not that much.
Okay. One last question here from Harry. Is there any evidence that cores can become more squishy in neutron stars orbiting one another? I'm not sure whether I understood the question. Harry, do you want to elaborate on the question?
Yeah, I'm just thinking about the graph that you had shown on that slide when you're talking about, I think you were comparing the nicer data with the gravitational wave data, I think.
Mhm.
And I was just wondering if the reason that there's kind of a split in that data would have been because maybe there's some effect on the neutron stars on one another when they're orbiting each other. I don't know.
Do you mean as they're merging?
Yeah.
Yeah, I mean, that's a good question. I think it's not probably fully explored, but I think the main thing that they're looking for when they're orbiting each other is just the deformation of the whole neutron star. Like, how much are they deforming as a whole? And
Okay.
then, as the more that they're able to deform, probably the more, squishy basically the matter is inside them. So
Okay, cool.
Okay.
If I could
maybe-
interrupt, I'm sorry, Mehmet, I had a question you missed up there.
Oh, sorry.
No, that's okay.
Go ahead, Dina. My
Okay.
screen may not show all the questions. Go ahead.
Right. No, I get it. That's okay. So you had a neutron star that you said emitted radiation from all over its surface instead of having jets at the poles. And I was wondering, does that mean that it is not spinning? And likewise, are there any black holes that don't seem to spin?
I think that they're still spinning, although we wouldn't have a way to measure the spin. But when you think about when you have a star-sized object, and stars rotate at some level, right? Like the sun rotates every 25 days, and then you collapse that down to a city-sized object, it's going to be spinning very fast when it's born. And so even if they slow down over time, they're still going to be spinning.
But I'd be mystified if they stop spinning.
Right. Yeah. So yeah, they definitely would still be spinning. How fast they're spinning, though, like magnetars, for example, generally spin slower, and that's neutron stars with very strong magnetic fields. And they will sometimes spin like every, I think the longest period that has been observed for pulsars anyway is 12 seconds. And understanding why it stops at 12 seconds is a bit of a mystery too. That's a different question. But yeah, so they should slow down beyond 12 seconds. But we haven't observed any pulsars that have periods slower than that.
Okay, thank you.
Joe Goodwin-Aston is asking a similar question, I think. How fast do neutron stars spin? Or did you get the answer to your question, Joe? Or do you want to expand on your question?
No, that's
That's
I'd
answered.
still like to know.
Go ahead.
Yeah, I mean, so 12 seconds is kind of the outer range, right? The fastest range we get is millisecond pulsars. And so those are the pulsars that go much faster than a kitchen blender. So there's a big range, but I mean, just for me, just the imagining a Manhattan-sized object spinning around, 100 times a second or 1,000 times a second is really incredible to imagine. So
Mind-blowing.
Yes.
Okay.
Okay. Well, are there any other questions? Did I miss any questions? I was just looking at the chat line here. Are there any other questions that people would like to raise their hands or voice their questions?
I don't see any others, Mehmet.
Okay. Well, in that case, thank you very much, Dr. Young. We really appreciate. We found it really very informative, and thank you very much for all your efforts and putting it together.
thank you very much for having me.
And also staying so late for you.
Oh yeah, no problem.
Okay. Thank you very much. We really appreciate it.
Yes, it was wonderful. Thank you. Thanks for staying up late for us. We appreciate you.
All right, thank you all.
We
Okay.
will continue with the meeting, Dr. Young. If you want to stay, you are welcome. But we would understand if you want to go back.
I think I am gonna head out now, but thank you so much for having me. It was a pleasure to be here.
Again, thank
Thank
you.
you.
Thank you. I appreciate it.
Bye.
Bye.
Okay.